Hi friends, hope you are doing well. Today we begin lecture 53 in our aerospace engineering course, and today I'm going to talk about the airplane longitudinal static stability, and today we are going to derive expressions. So these are going to be quantitative explanations about the reason why a horizontal tail is typically present in an aircraft and how this has an impact on the stability of the system, specifically the longitudinal static stability. So we are going to look at the aircraft in pitch motion. So let's first start with the wing section, and then we are going to look at the wing body, and then we are going to look at the tail. So if you look at the wing section here, I have made this airfoil in yellow. And so let's look at some of the geometry and then some of the forces which act on this airfoil. So essentially this airfoil has chord given by C, and the CG of the aircraft is at this location here. CG is mentioned, and so you can see that this CG is at a distance h into C from the leading edge of the airfoil or the wing. Similarly, the aerodynamic center is located at this point here, which is typically the quarter chord, and this is at a distance HAC WC from the leading edge of the wing. Also, you clearly see that the air velocity is coming here. This is V infinity, and this angle is alpha subscript W, where W stands for the wing. Now do remember, here we are looking at the absolute angle, so it's relative to the line, which is the zero lift line. Now when you have an airfoil or wing section like this, you are going to get the usual lift and the drag. So these are given by L subscript W and D subscript W, and of course you also have the pitching moment which acts at the aerodynamic center about the quarter chord point. So this is MAC subscript W. So here all these W mean wing, and also you have this CG at a distance Z into C from the zero lift line. So that's another fact about geometry which we need to consider here. So this is essentially the wing, and now we are going to look at this further and look at what is the contribution of the wing to the CG pitching moment. So let's look at that here. So if we take the moments about the CG or the center of gravity, we are going to get the moment coming from the aerodynamic center point here. Then we are going to get LW into cos alpha, which is the component in the vertical direction, into HC minus HACWC. So that's this distance here. That's the moment arm for the lift LW. Similarly, we are going to take dW, we are going to take the sine component, that's again the vertical component of dW. So that's going to have the same moment arm HC minus HAC W into C. Then we are going to have the components which are in the horizontal direction. So there is going to be LW into sine alpha, that's the component in this direction, and so that's going to get multiplied by ZC, and finally we have the drag component D into cos alpha, which is in this direction, and this is again multiplied by ZC. So do remember that when we are considering sines here, we are considering the pitch up moment to be positive. Therefore, for example, the lift in the vertical direction acts like this tends to pitch up, so it's a positive component. Similarly, if we look at this particular component of drag, dw cos alpha, that's in this direction here, in the horizontal direction backward. So this will essentially go nose down or pitch down. So this is the negative moment. All the remaining are generally positive here, and of course MAC will have whatever sign it does depending on the particular airfoil we are considering. So now let's try to simplify some of the algebra which we had, or the trigonometry I should say. So let's start with the fact that if alpha W is small, and it typically is small because most conventional airplanes will fly at some angle like 5 degrees or even below that. So what would happen? Cos alpha would be 1 and sine alpha would be simply alpha itself here. So again W subscript simply means we are referring to the wing in all these conditions. So now with this particular simplification, I can take the equation we derived before, that was for the mcgw, and I can replace this cos alpha by 1 and I can replace this sin alpha by alpha. And so if we do that, we get this equation here. So there is a substantial simplification in the equation here. So essentially you get this term Lw plus Tw into alpha W, that's this here, and then here you get Lw into alpha W minus Tw, so that's the term here into Zc. So now this is the moment about the CG caused by the wing. So what we can do is we can non-dimensionalize this, we can get the coefficient here. So this is the pitching coefficient, pitching moment coefficient, and this is essentially the moment divided by Q infinity SC, where Q infinity would be the dynamic pressure, S would be the area of the wing, C is the chord of the wing. And so if we were to divide this equation throughout, we get this equation in terms of the coefficients for the pitching moment. The lift and drag becomes coefficient of the lift and the coefficient of the drag. These are CL and CD. And so this is the equation here. There is some division in terms of C also. So some of these C vanish. So now you can see why we had kept this H into C and Z into C type of nomenclature, so that we got a clean expression here for CMCGW. Now let's do some further simplification. Now for many airplanes, this Z distance is also small. That is the distance from this zero lift line to the CG. This distance is relatively small. Also, we will see that generally alpha W is much smaller than 1 if we are considering radians. So CDW into alpha W is much less than CLW. So what this lets us do, it lets us get rid of the Z term because Z is essentially very small, we will just neglect it. And also this term involving CDW into alpha W, we are simply going to drop this. So what you are going to get is you are going to get this moment term here, CMACW, and you are going to get simply the CLW term multiplied by H minus HACW. So that's the term which I finally obtained here after the approximations we have made before. And so what this lets us do is that it lets us calculate the main effects of the model. So essentially we started with a model which had a lot of detail, and then we realized that for many actual aircraft configurations, many conventional aircraft configurations, we can make a lot of simplifications. And so after all that, we obtained this simple equation here, that CmCgW equals CmACW plus CLW H minus HACW. Now do remember here that CLW is dCLW by d alpha into alpha W, or we can write it as A subscript W into alpha W. So remember, A is the lift curve slope and W again refers to wing. Alpha is the absolute angle of attack, and W again refers to the wing here. So with these now we can make further simplifications, but before that let me just point out that H minus HACW is the moment arm. So we are going to take a look at that again. That's something which is very important from this equation point of view, because the lift component is getting multiplied by this moment arm. So let's take a look at this figure again and recapitulate as to what is H minus HACW. So you can clearly see that HC was this distance, HACW was this distance. So essentially H minus HACW would be the distance between the aerodynamic center and the center of gravity. So that's the distance we are considering here. So this plays a very important role, and on top of that you of course have the pitching moment about the aerodynamic center also. So these together contribute to the wing component of the pitching moment about the CG. So one component is coming because of the moment about the aerodynamic center, and the second component is due to the lift and the distance between the aerodynamic center and the CG of the aircraft. Now we are going to make a certain expansion in our thought process. We are going to consider that there is a wing body, and the wing body is actually the concept which says that the fuselage and the wing, if they are joined together, they would create a certain flight system which can be called the wing body. So what we do is we take the contribution of the wing which we derived in the previous few lectures, and I have put in this light blue box here, and then we simply change the W to WB here, which means wing body. So each of these expressions is simply changed slightly. And what would happen now is that we would need all these new coefficients and so on. These are very difficult to get theoretically, so they are often obtained from wind tunnel tests. Now, whenever we add fuselage to the wing, several things are going to happen. The aerodynamic center is going to shift forward. There is going to be an increase in the lift curve slope, and also there are going to be changes in the moment about the aerodynamic center. But beside these things, the basic form of the equation remains same, only the coefficient values are going to change slightly, and that we are going to obtain from the wind tunnel tests. So now let's start looking at the tail. So this is the picture of the tail here, and in fact when you consider the tail of the typical airplane, you can presume that this is a symmetric section. So this is very common that the tail wing sections are symmetric. Alpha t is the absolute alpha of the tail. So again you can see here that the velocity which was there, v infinity, which was present in the wing or the wing body, is now shifted to this value v dash, and this v dash is present because there is a downwash of the finite wing which is hitting the tail, and therefore this inclination by the downwash angle epsilon is there, epsilon being the angle between v dash and v infinity. So it's important to get a hang of this nomenclature because it's kind of detailed, and you can clearly see that if you look at v dash, the drag in the tail, the lift in the tail, dt and lt will be parallel and perpendicular to this v dash respectively. So that's something to keep in mind, and these angles are the epsilon here, which is the downwash angle. And also remember that alpha t is with respect to the zero lift line of the tail, and the v dash velocity, which is the velocity which the tail actually sees. The tail does not see v infinity, the tail sees v dash. So just as a point, I should mention that there is a small contribution of the lift to the total airplane lift, and we can generally assume that this is given by LT because epsilon is typically small, it's very small, and therefore cos of epsilon would simply be 1, sine of epsilon would be negligible, and so we can say that there would be a contribution LT from the tail. Now let's get to the fact as to why the tail actually exists. We know that tail is there to enhance the longitudinal static stability. So let's look at the wing body and also combine the tail here. So like I mentioned before, but now when we look at the wing body, the angle which is seen becomes alpha subscript WB, referring to the wing body. This is the airflow at V infinity. The CG of the aircraft is here. This is the tail. Now this diagram is such that all these things are expanded out. Obviously the tail may not be so big with respect to the wing, but I have just tried to fit all these things into one slide when I made this drawing. Now the tail has a particular angle I subscript t, which is the tail setting angle, and here you are also seeing the velocity v dash. The angle here is alpha t, and so the tail has several different forces which act on it. There is the lift force, there is the drag force, and then there is also the pitching moment component here. Now do see that relative to CG here, you have a distance LT between the CG and the aerodynamic center of the tail, and the distance between CG and the aerodynamic center in the vertical sense is given by Z subscript T. So these are some nomenclatures we are going to use. So now what we do is we get the moment contribution caused by the tail. So if you want to do that, you take MCG, you'll clearly see that there is going to be a component LT cos alpha WB minus epsilon. So that's the angle here. So LT would be, the LT cos alpha component would be in this direction, and then there would be a drag sine component that would also be in this direction, and then these would get multiplied by the moment arm LT here, and so this component is then going to be given a negative sign because remember pitch up moment is positive, pitch down moments are negative. So similarly, there is going to be a contribution LT into sine, that's in this direction. There's a component DT into cos, that's in this direction here. So now with all those components out there, we can write this equation out, and also remember that MACT is the tail contribution as far as the moment is concerned, the pitching moment about the aerodynamic center. So all these forces are of course acting at the aerodynamic center. LT is normal to V dash and DT is parallel to V dash. So with this MCG out here, we can proceed forward and try to simplify this equation, because this angle is typically small, and so we can do a lot of simplification here. So what we are going to assume for a conventional airplane is that Z is much lesser than LT, or ZT is much lesser than LT, and also DT is much lesser than LT. Now also remember this alpha WB minus epsilon is small, and so I can write MCGT is minus LT into capital LT here. So LT is the moment arm and capital LT is the lift generated by the tail. Now I can put this in non-dimensional form as far as the LT is concerned. CLT would be LT by Q infinity ST. So do remember here Q infinity is the dynamic pressure, ST is the area of cross section of the tail. Now from this I can get mcg tail equals negative LT Q infinity SCLT. So all I have done is I have taken the LT here and I have put it here, so I can express mcg tail in terms of CLT. Now do remember that the wing sections are typically symmetric, so I can simply ignore the MACT here also, because that would be essentially close to zero for a symmetric section. So now let's continue on our simplification journey. So we get MCG in this form, and we can then immediately write CMCG by non-dimensionalizing the MCG by Q infinity SC, and that gives me this simple expression here in terms of LT, ST, C and S, and this particular term is known as the tail volume ratio. So that's defined as V subscript H is LT into ST divided by C into S. So essentially this is telling you how much of the tail volume is there with respect to the wing volume. So remember C and S are coming from the wing. So with this I can very quickly write CM CG tail is minus VH into CLT. That's nothing but this equation being written here. So finally I obtain a very simple form of this equation after making all those approximations about small angles, small distances and so on. And also now to remember the fact that alpha t was alpha wb minus it minus epsilon. Alpha t was the angle at the tail, alpha wb was the angle at the wing body, it was the incidence of the tail, epsilon was the downwash. So from that I can now write CLT is AT into alpha t. AT is the lift curve slope of the tail, alpha t is the angle, and therefore I get this equation here. This equation is important to remember because it will clearly tell you that if you were to increase IT substantially, you would start getting negative lift, which is something you may need for static stability. So now we can get the moment contribution by the tail in this manner, and what often happens is that this epsilon value can be obtained from wind tunnel test, and it is found that this itself is a function of a constant part given by epsilon 0 and a part which is a function of alpha WB. So we can write this out here. So I took this CLT here, I put epsilon here and got this equation here, and then remember again that MCGT was minus VH CLT, and so if I substitute the CLT value here, I get this equation here. So now this equation is becoming something which we are finally going to use for our stability calculations. So now it's time to combine the wing body with the tail. So the total pitching moment about CG is given by CMCG here, and also we can now clearly write it in this form. So there is the component because of CMAC wing body, there is a component because of the lift wing body, and the distance between the aerodynamic center of the wing and the airplane CG, and there is the tail component given by VHCLT. So if we expand that out, I get this pretty large expression in the yellow box, which is actually the expression for CMCG, and now we are going to use this for our further calculations. So just one point to mention here is that there is a difference between the airplane and the wing body, and wind tunnel data when they are obtained are typically giving coefficients for the complete airplane, but for most conventional airplanes this difference is pretty small. So for example, if the airplane is flying like this, that would be an alpha wing body, there would be an alpha airplane. These would be slightly different. For our purposes, we are going to assume that these are basically same. Again, it's one of the simplifications we are making to simplify our life and our formulas. So alpha WB is alpha A, which is the whole airplane. CL WB is CL. AWB, that is the lift curve slope, is simply A. So from this, I take the equation I derived before, which is in the yellow box, and I replace it in this form. So here I have replaced WB by A. Again, here I have replaced the WB by A here, and I have got this simpler equation out here. Now what we are going to do is we are going to take this equation here, and we of course know that Cm0 can be obtained by taking this Cmcg and putting lift is 0, which would be same as putting alpha A equal to 0. So if I were to put that, this entire term would vanish. So I would get Cm0 would be Cmacwb plus Vh At It plus epsilon 0. So now of course we know that this Cm0 must be positive. We also know that typically Cmacwb is going to be negative for a conventional airplane because cambered airfoils will have a negative Cmac. So therefore this component involving Vh must be positive and sufficiently large. Now do remember Vh is dependent on the tail volume ratio. All these numbers are essentially going to be positive if you have placed the tail backward, and therefore what you have to do is that if Vh is positive, At is of course positive, that's the lift curve slope for the tail. Epsilon 0 is a very small number. Your It must be greater than 0, and it should be tailored such that Cm0 is a positive number. Similarly, if we look at the slope, so again, if I take the equation for CmCg and I were to differentiate it with respect to alpha A, I would simply get this term here. So this is nothing but the coefficient of A here, and so this should be less than 0. Now for this to be less than 0, I can obtain all these different values from wind tunnel data, for example At, this derivative here, Cmacwb, and so on. And what I can try to do is to make this particular term pretty large. So what you do is you make large VH, you make therefore a large value of LT divided by CS. CG of course may not be something you can do too much about, but if you can do, then that would be something you can also use to control the situation here and ensure that this derivative stays negative, because that's a requirement for longitudinal static stability. If you are not familiar with that, go back to my previous lecture and look at the qualitative analysis on how this is possible. This was done in lecture previously we did with the qualitative approach. So therefore the value of IT, which is also tunable, will play a role here, and so with all those factors you have to somehow ensure that this value stays negative. So basically, to summarize today's pretty intense lecture, we find that at the end of the day what happens is that you have the wing body, you have the tail, and you need to tailor the different parameters to ensure that the tail produces a moment such that the conditions for longitudinal stability are satisfied. The parameters which you can control are LT, that's the difference between distance between the CG and the aerodynamic center here, ST, which is the area of the wing, and I subscript T, which is the incidence of the tail with respect to this zero lift line. So always remember CLT is essentially dependent on AT and alpha WB, IT, and epsilon. And so IT is going to play a very important role here. If you increase IT, you can create negative lift, and if you can create negative lift, you can stabilize the airplane in terms of longitudinal static stability. So this was the quantitative explanation of whatever we did in the last class in terms of the qualitative explanation for longitudinal static stability. You saw clearly that the placement of the tail behind the CG is very important as far as aircraft is concerned, and therefore you will see that aircraft will typically fly around with horizontal tail. Of course, you can do this derivation for the canard also. The derivation will be different and you will get something similar, but then the lift on the canard will go up, and in the horizontal tail it goes down. So I'll end this lecture today. Be sure to understand the geometry of the bodies very well, because they do play a very important role in this derivation. And if you have any questions, you can put it in the comments below, and I will try to answer those questions there. If you are interested in problems, of course, refer to Anderson's book for solved examples and problems on this particular chapter. I'll end this video now, and I will see you in a lecture sometime soon. See you then.